Yes, we see you.
Yeah, thank you very much. So I would like to tell you today about topic which is quite important from the general point of view now, and it will be much more important in the future. Because I work at the Lodz University of Technology and the Textile faculty, so we're working with fibers. And I work quite a long time at this faculty, and I made some observations concerning that the global market of fibers will be completely different very soon. So from the beginning, I mean, we people, I mean, the humankind, started. I would like to start with some historical background. So I would like to say that firstly, people started using natural fibers, because you must know, and it is quite important, that wearing clothes is a very important, one of the most basic needs of people. Our first need is to have food and to not to be hungry. The second is to feel secure. The third one is probably to have some companion to live in the group, in the family group or in the bigger group. And just after that, we have very important need concerning wearing clothes. So important part of our life are clothes and fibers. Of course, currently we are not using fibers only for clothing, but we rather using textiles for many technical applications. But still, we need millions of tons of fibers every year. We still, I mean, humankind. So firstly, we used animal skins. Shortly after that, it appeared wovens and knitted fabrics made from natural fibers. This is a curve which is showing the number of people in the world in last 60 years. So you can see how fast is increasing the number of people. But as you know, our Earth has still the same size. So the arable area cannot be bigger than it is now. So we can increase the arable area a little by eliminating of woods or something like that, but it is not the best way probably. So currently we have still the same area of arable agriculture. So that means that there is a big competition between cultivating of food and cultivating of natural fibers, because every natural fiber need some arable area, like for example cotton, like wool, like silk. These are the first types of fibers which people used in the past. But always it is connected with using some arable areas. But as I said, the natural fibers will be more expensive, are quite expensive now, but it will be more expensive in the future because we will prefer rather to use our fields and our arable areas to cultivate food than, because it is more important, than to have fibers for people there. So it means that we must to use chemical fibers. It is our obligation, and we will do it. Coming back shortly to the history, in ancient Greece, people used wovens which were made from wool and linen. Just after that appeared wovens made from cotton, which were imported from East. And currently, we have such sources of materials. Natural, like produced by plants, cotton, or those produced by animals like wood or silk. Or there is a second part of fibers. On the right side, you can see chemical fibers. Chemical fibers has such advantage that we can produce this in the factories. The factories take small area, so we can produce big number of fibers every year in small limited area. So we don't need to take very big areas to produce fibers. So there is a big advantage of production connected with production of chemical fibers, like this, that we have we can produce fibers with properties which are exactly closely connected with our needs. So we can produce exactly this product, which is good for us. So this production is repeatable. So after every step, after every year, after every day, we can produce the same quality of fibers, which is not so easy in the nature, because in the nature, we have every year a little different weather. We have geographically, there are some geographic difficulties and differences, but in the factory we can produce always the same fibers with the same properties. So it is important advantage. And also production is fast. Sources, I mean polymers for the production of fibers, are quite cheap, so the production is cheap as well. But there is one problem with production of chemical fibers. They're typically not biodegradable. You can see red colored materials here, like mineral fibers, organic and inorganic fibers, which are not biodegradable. There is one example. There's only one type of chemical fibers currently, which can be which are biodegradable. These are regenerated fabrics. This is the name of the viscose fibers, but production of viscose fibers is not currently developed, because this is very harmful for the environment. But the production of chemical fibers is good because it's cheap, it's fast, it's repeatable, and it's not taking arable area for food, but we are producing not biodegradable fibers. So it means that we are producing increasing number of the trash. So it's a big problem because these products cannot be utilized very easily. And it may be harmless for the natural environment. Besides those properties which I mentioned of natural fibers, there's another very important group of properties. So this is the easy access to resources, price, fastness, and possible customization. This is what I said. And also chemical fibers have very good mechanical properties. I mean, the durability of chemical fibers is very good. And we can produce chemical fibers with such mechanical properties as we wish. As I said, one way of the production, currently one really developed way of the production of the chemical fibers which are biodegradable is the production of viscose fibers. Viscose fibers, the substrate of the production of this material is cellulose, which is taken from wood, from trees, and we can do it. We can produce cellulose fibers in the factory by using chemical methodology. But here you can see that there is quite complicated, long process containing many steps. And unfortunately, the main problem of the production of viscose fibers is that during this procedure, we have the emission of toxic gases. So this is very problematic. And if I remember well, the production of chemical fibers in Europe is already forbidden. So there is no, the production of viscose fibers, but using the traditional methodology is forbidden. And so that means that this is impossible for the biggest scale, for the right scale currently. We would like to have biodegradable fibers because there is a large group of textile materials like disposable textiles for hygienic reasons, which creates a big amount of wastes. This is the production of millions of tons every year, every month even. And there is no way to do something with this. So recycling of the disposable textiles is impossible. So the only way is storage and waiting for the natural biodegradation. If we would think about the coming back to the natural fibers, like wool or cotton, I must say that it is impossible because the proportion between chemical and natural fibers is currently on the side of chemical fibers. So in 2005, the global production of fibers, 52% were chemical fibers, and synthetic, I mean not viscose fibers, it was 92% from this group. So now the proportion is probably even more on the side of chemical fibers. We have some methods of the production of chemical fibers. If it's possible, always we want to produce these fibers by using melting technique. So we want to have thermoplastic polymers, because it's cheap, fast. And another advantage, which I didn't say till now, of the chemical fibers is that we can have those chemical fibers or resistance to microorganisms. So using them, it's typically more hygienic in contrary to natural fibers. But this, on the other side, it may be a problem because they're not biodegradable. This is the reason of this, that they are not biodegradable, because because they are resistant to microorganisms, and that's the circle is closed. And here you can compare the time of biodegradation of different materials. You can see that the fastest time is for paper towel, it's between 2 and 4 weeks. Newspaper, 6 weeks, cardboard box is 2 months, and this. But for example, for plastic bottle, it may be about 100 years. For disposable diapers, between 50 and 100 years. Tin can, it can have 50 years. Aluminium can, 200 years, and monofilament fishing line, it may be even 600 years. We don't know so long polyamide fishing lanes, so we are not sure that it is 600 years, but this is of course some kind of approximation, and the effect of the testing in the laboratory, the degradation testing in the laboratory. So you can see these periods may be very long, and this is the problematic. But I don't want to complain here and to create problems, but I would like to propose you some solution for this, because we can produce some kind of thermoplastic polymers which are completely biodegradable in the environmental conditions, like aliphatic polyesters, made from different monomers like glycolic acid, lactic acid, butyric acid, or caprolactone. And polylactic fibers, here you can see the structure of the polylactic acid. Polylactic fibers are already used for some applications, like implants and surgical treats. We can produce these materials from polylactic acid. And we know quite long polylactide. Polylactide was commercially produced by Carothers in 1932. And now we know this polymer very well because it's almost 100 years, more than 100 years. We have several industrial ways to obtain the polylactic fibers. The monomer for the production, for the polymerization is lactic acid, and it may be cyclic diester lactide. So you can see here two main ways of the production of the polycondensation, but you can see that the most important thing is that the source, the first substrate, which is used in the production of polylactide, are plants. This is the plant. So it's really good information that we can use plants. We are using photosynthesis to produce plants. After that, we are producing carbohydrates. Bacteria on the fermentation way are producing lactic acid. And by using proper catalysts, we are obtaining a polylactide by the polymerization or polycondensation methodology. So we can choose. The melting point for typical polylactide is about 180 degrees Celsius. Glass temperature about 55. But the problem, this is the prices from some years ago, so I don't know current price, but that time it was the price of 1 kilogram, it was about €2. So it was the problem because it means that the polylactide was really expensive in comparison to polyolefins, for example. So the most common route to production of polylactic acid is the ring opening polymerization of lactide with various metal catalysis like Keynote state in solution in melt or in the suspension. So as I said, we know many methods of the production, but there is some problem with this thin catalyzation process. But this, what I'm showing you, this is the typical way, but we know different catalysts now. Okay. And I would like now to compare the properties, the mechanical properties of polylactide fibers with other popular polymers like polyethylene, polypropylene, or polyethylene terephthalate. Let's look at the tensile strength. You can see that we have 570 for polylactide, so a little lower than polyethylene terephthalate, but this difference is not very big. So all of this depends on the final application. Elongation rate about 30%, so between polypropylene and polyethylene terephthalate. And Young modulus is about 6 gigapascals, so not far from polyethylene. So it means that this polylactide, which we can produce, has properties really close to typical polyolefins or other synthetic polymers. Big advantage of polylactide is that we can produce polylactic fibers by using exactly the same technical equipment which is used for polyolefins and for typical thermoplastic polymers. So exactly the same machines. So the melting temperature, maybe we can change, we can control the melting temperature, and we can produce the polylactide fibers in different form. The first one is just a typical fiber, but the second form on the right side, you can see that we can produce directly. So during the polymerization process, we can produce fibers, not fibers, but we can produce the non-woven, which is flat textile product. So it may be one step faster. For some reasons, it may be a really important advantage. So as I said, polylactide was used for surgery treats. For some applications in medicine, so we can produce nanofibers made from polylactide. You can see here the comparison between nanofibers, between nanofiber and the human hair. We can produce capsules from polylactide, and medicine is inside of this capsule. But what I would like to propose to produce from polylactide. So some kind of upholstery, disposable garments, awnings, feminine hygienic products, and most importantly, diapers. So there is a group of products which in which the production of the using of biodegradable material is very important, because we cannot recycle such products. So it is very important to use product which is biodegradable here. Besides more advanced applications like screws, pins, rods, and even mesh against hernia. So some kind of application inside human body can be produced from polylactide as a very good alternative. This advanced applications, like we can see here, for these applications, the price of polylactide is not really high. But I think that in the future, polylactide will be an object of the most common production, like cups or bags, even we will produce from polylactide. But we must be sure that it will be a little more expensive than currently production of these products from polyolefins. So tableware, good quality tableware, and also things for food. So food packaging can be produced from polylactide. We can produce clothes if we want. It is responsible again X radiation, so microwave waves can be used. We can use hot fill application. Some kind of engineering fabrics can be also produced from polylactides. I'm not a biologist, so I don't want to discuss the biodegradation of the polylactides. So, but I would like only to mention that the classical mechanism of microorganism of polylactide degradation is the mechanism in which we have the attack of enzymes on the macromolecule. As effect of this attack, we have the cutting of the macromolecule into smaller part, and finally we are obtaining we have a kind of depolymerization, of advanced depolymerization or hydrolysis, and the effect of this procedure, we will have low molecular weight products. So if the conditions would be good, so for some cases, for some reasons, we can try to use the lactide, which is the product of the depolymerization here, we can use again for the production of something new. Not always, not for diapers, for example, not for kind of composites, but for some materials produced only from polylactide, it may be a good solution to try to initialize recycling of the polylactide. What is important when we think about the degradation or biodegradation of polylactide is that the degradation of the polylactide can be really different because of the external conditions. So it's very the external conditions can change the biodegradation time really fast. So it may be, the degradation may be fast or it may be slow. So we can use the material quite long time or quite short time. And I think that it is one of the biggest advantages connected with the using of polylactide fibers. to control the biodegradation, because we want to have we want to make the biodegradation of that material, but it cannot be too fast, so it must be controllable. But unfortunately, it strongly depends on the external conditions. So it is temperature dependent, it's humidity dependent, and also some kind of mechanical factors can have influence on it. I can summarize this part that it can take between a couple of weeks to many years. And yes, and it should be controllable, but now it's some kind of challenge. Okay. This is the example of the chemical hydrolysis or the enzymatic hydrolysis of the polylactide. I said already. So the mechanism of the chemical hydrolysis is the point of discussion, but I think that we can say that firstly we have the decomposition of the ester bond as an effect of nucleophilic attack of the external factors, and finally we have the acidic catalysis process. But this is not very important from the final efficiency, but the mechanism is important because of the time of degradation. Okay, going to the end, I would like to mention only about some methods of the changing of the properties of the polylactide materials, because the modifications methods of polymers are currently very developed. So even almost each materials or multi-layered materials or modified materials or grafted materials, etc. So I would like, I and my colleagues, of course, because why I'm generally wanted to tell you about this polylactide to you today. The reason is that we had a project which was called Biogratex. It took about 8 years. We finished 3 or 4 years ago. And yes, and looking at this, it's not our experience with introducing of the polylactide fibers into the textile applications, into the different textile applications. I can say that our big experience in this topic can suggest that the polylactide will be very good future material for textile applications, but not only, of course, for textiles, but also in different applications in which we can replace typical thermoplastic polymers. But as I said, we made some tests concerning the modification of mostly on the modification of the external surface, not about the whole volume of the material, but about the external surface. The first way was the grafting, because the external layer of the material can be produced, can be strongly changed by the grafting, because we have here the connection. This is the grafting copolymerization, so we can connect different type of polymer by the main chemical bond. So it's very efficient, very easy. Typically, it's cheap, and yes, and we can introduce different polymers as a layers, as an external layer. The most of our modifications was concerning of the introduction of the polyacrylic acid. That was the basic material, and we changed the conditions of the grafted copolymerization, and we confirmed that it is possible, and the final effect strongly depends on the conditions of the procedure. Okay. The next one is entrapment, which is even more easy than grafting. So entrapment idea, I'm not sure you're familiar with the entrapment idea is that we are taking the polymer into the mixture of the solvent and no-solvent. After such treatment, the external layer is more delicate, is more soft. So after such swelling, we can introduce the solution of the polymer, which we want to entrap inside. And after entrapments, we are taking the material into the non-solvent, and thanks to that, we can have the modified layer. It's just a physical modification. There is no chemical connection between those materials, but it's very efficient, easy, cheap, fast, and the durable modification. So even it depends on the entrapment conditions, but we can change the surface. So when we can introduce the polyacrylic acid, I think that many other options are possible. Here, there's example of sodium alginate introduction, and the polyaniline we can try to introduce, so different polymers can be introduced on the surface, and even very easy, just the easiest way of the modification, like padding. So we're taking the material into the some kind of solution, and after that we are looking what is happening. And here, of course, the substrate must be polyacrylic acid, not acrylic acid. And it is possible only to use for disposable materials, not for multi-using, not for washing. But we can do it. We can introduce as well some kind of amines to control the hydrophilicity of the sample. It strongly depends on the external conditions. So padding is maybe not a very sophisticated method, but in the industry, they like it because it's easy and cheap. And maybe it's not impressive, but cheap. And yes, and the last method which I would like to introduce is using the layer by layer technique, which is not the was proposed by Gio Decker about 25 years ago, but he did it. He applied this method for mica, for metals, gold, silver, etc., but not for textiles. But we use this methodology for textiles. Of course, to apply this methodology, we need to have a charged surface. Polylactide is not charged, so we use the grafting methods for introduce charging as a first layer. So the source of charge was polyacrylic acid, and thanks to that, we create such structure, such multi-layer structure to control the external layer of the material in bigger way. The advantage of this methodology is that it's as well quite easy, but not so easy as padding. But we don't need to very hard solutions, because it's the layer by layer deposition is in the room temperature, and the concentrations must be very low. Time is short, and we are using the water as a solvent. So in this way, we introduce polyacrylic acid, polyallylamine, and different polyamines. So for polymers, we introduce here 4 polymers as an external layer, and we confirm the structure by using coloring tests. Here, we controlled this color. Let's see examples. And finally, we obtained a system of containing 5 layers. So it's probably such multi-layer system is rather kind of scientific experience, maybe with not big practical meaning. But if you want to obtain a product with very strongly known properties, it may be a good way to increase the number of layers during the modification. Of course, the modification is changing as well electric charge, electrokinetic properties, and in one way we introduce the polyaniline on the surface to obtain surface with it was the procedure of in situ polymerisation, and we obtain in this way surface further. with polyaniline on the external layer. Okay, and the last property which I would like to show you. So we can change the hydrophilicity, we can change during the surface modification, we can make electric conductivity, and even we can change the thermal resistance of the material, because the deposition of different number of layers can increase the thermal stability. What was a little surprising, because the thermal properties are not the surface properties, there are volumetric properties, but it appeared that we can change this very delicate surface modification, can change even thermal properties. So it was something what was surprising. And okay, I think that I'm on time. I try not to talk too long. So thank you for your kind attention. And if you want to ask me, I would be glad to answer any questions.
Yes. Thank you, Dr. David, for your wonderful presentation. So the floor is ready for discussion. So is there anyone to ask doubts to Dr. David?
I can ask you, David. As I understood correctly, so if we introduce PLA into the body, like for different purposes, it will decompose just due to the enzyme interactions. So
yes.
And how long it will take it to decompose?
It depends on the place in our body. It depends on the conditions in the body in which it is. The important investigation in this question was connected with using meshes against hernia instead of polypropylene against hernia. When we have you know the hernia, it's a I don't know how, so different. So when you have in the stomach problems, we can introduce into your stomach the mesh to inside the body. So typically they are using polypropylene meshes, which are staying inside the stomach to the end of the life of the person. But it's much better when the degradation, when the mesh will degrade. So this is much better generally, but the time of degradation should be long enough to close the problem, and not as long as person is living. So it should be estimated in between 6 and 8 weeks. This is the minimal time, but typically it's longer. But unfortunately, it creates some states which can be not good for the body. But I think that generally it will degrade in the body, and the time of degradation depends on the place in the body in which it is placed.
Is it already used? PLA already used for this stomach problem?
Yes. Yes.
I also heard that PLA was used for stents. Do you know what was the problem with this material? It is not used anymore.
I don't know. I'm sorry, I have heard, but I don't know. I know we used the foil produced from polylactide. It is our experience on the agriculture, to cover the field. But the problem was that we didn't want to remove this, because the plan was that we will use this on the fields of the agriculture field, and after degradation it will be in the soil to make better, this better for the soil. But the problem was again with the weather, because one year the weather was sunny and rainy, and the degradation or is different when it's dry or Yeah, so it depends.
Yeah, it's exactly the problem to use this material for clothes or different things around. So as you explain about this functionalization, do you think this functionalization can make this material more stable and degrade whenever we want it to be degraded?
Yes, because the surface modification, firstly, we can control the properties of the polylactide during the production stage, because the degree of crystallinity may be different. So by controlling of the degree of crystallinity and the type of crystallines, we can also control the degradation time. But as you said, the introduction of the external layers also creates some insulating layers between the external parameters, external factors, and the main material. So that means that it will be it may be a factor for the controlling of the degradation. Okay.
Thank you. Thank you very much.
Thank you very much.
Yeah, thank you so much.